So if we're going to do an SN2 reaction, so one of the pieces of evidence we had for an SN2 reaction was that inversion of stereochemistry, right? Inversion of stereochem. Right? Inversion of stereochemistry. So what that means, right, we essentially what someone did, they ran a reaction. And let's say they had a molecule like this. This could be H, this will be ethyl, and this will be methyl. So, this molecule has a stereocenter, or an asymmetric center. So what does that mean? What's an asymmetric center? Has to have 4 different things bind to it, and what hybridization state? Has to be sp3, right? Inherently, that's kind of one and two the same. Now we're adding a second caveat. It has to have a good leaving group attached to it too, right? Because right, for all these reactions, we're doing a substitution, so we have to substitute something for this, right? So if I add in, somebody pick a nucleophile, let's say OH minus, as in somebody, as in me, right? Yeah, so that's what we're going to look at, right? So should we also figure out whether this is R or S? Let's do that too, right? So let's rank these things to figure out R and S. So which one's the highest ranked? BR, so we put a little 1 next to that guy. Lowest ranked? H. 4 is indeed the lowest ranked. Then ethyl versus methyl. Methyl is 3, ethyl's 2. Now, ideally, you'd all have your little molecules, but I can do this in my head. Did anybody see it yet? Mm-hmm. What is it?
Clockwise R.
S.
Wait,
What is
1,
this?
2. Isn't that R?
It's S, it's left, isn't it?
I don't know when
It's
you
counterclockwise.
It's S.
Oh yeah, because I'm looking at it.
It's S.
Do we need our models for tomorrow?
You can use your models. If I looked at this and I go, if I pull this 4, 1, 2, 3, it's S. So it's S. So what's going to happen now in the second step, so let's watch our nucleophile attack, of course, sigma star from the backside attack. The electrons from the carbon-bromine bond break. And what happens now is that we've flipped it almost like an umbrella. Right? So the bromine, or the bromine's gone, right? And let's say here forward is still the ethyl, and going back is still the methyl. And H is here, and now OH is here. Plus Br minus. Now, though, somebody should say, well, how do I know I did this right? How would you know if you did this right?
Isn't it just from here?
So it should be R. So let's check to make sure it's R. I could have done this wrong. I don't know if I did right or wrong. Let's rank these again. H is 4, OH is 1, 2, 3. So is this R now or S? It's R now. So did I do it right? That's how you know you did it right. So it's not just about, right, if you're worried about drawing it correctly, at the end of the day, there's lots of ways you could draw it as long as it's in the right stereo conformation. Right? I could draw R. I could draw this a little different, right, with different wedges and hatches, but it still has to be R. Make sense? So this was a piece of evidence that they used to say, oh, how can an SN2 reaction, how do I know this type of mechanism is going on, right? I know this because I'm inverting the stereochemistry, so that leads credence to say this mechanism takes place in one step, and it's always a backside attack, and that's why it does an inversion, right? So that was that piece of evidence, right? How do we figure out this mechanism, right? This is all the data they collected and said, oh, what does this data mean to us? All right, let's talk some about solvents. So let's break solvents into 2 categories, right? We can either talk about solvents as polar solvents versus nonpolar solvents. So in class, we exclusively talked about polar solvents because most reactions take place in polar solvents. Most reactions involve, right, delta plus, delta minus polar bonds. So it just makes sense that most reactions would be involved in polar solvents, right? So there's two types of polar solvents we talked about. One type was polar protic, which essentially was what? What does protic mean? You can, what kind of bond? It can H bond with itself, right? Which would include then things like anything with an OH, things with NHs, SH, etc. Any of those kind of polar bonds to hydrogen, right? Hydrogen bonded to a more electronegative atom. Now carbon and carbon-hydrogen bonds are pretty strong, right? We're sitting here, right? I'm not reacting. At least my carbon-hydrogen bonds aren't reacting. So those are pretty strong bonds. So those aren't considered polar bonds to hydrogen. So OH, NH, SH, hydrogen bonds themselves. Those are protic solvents. The other type of solvents we can have, of course, then are aprotic. Also polar solvents, not going to do the hydrogen bonding, right, with themselves. So what are some examples of polar solvents we had? Polar protic solvents. Ethyl acetate. Can't be ethanol, right? Ethanol can polar bond with itself. Yep. We could have acetone. We could have diethyl ether.
Is acetic acid word?
Acetic acid has an OH.
Yeah.
That's a protic solvent then, right? Alright. What other kind of solvents? And the new ones I introduced to you guys, the really polar aprotic solvents were DMF and the DMSO. Right? So there's some examples, right? Most times, and something I'm probably getting to a little bit more, right? We haven't quite got down to really breaking down conditions, right? So what I've done so far is I presented SN2 to you guys, and I showed you all the evidence for the mechanism. I presented SN1 to you guys, and I showed you all the evidence for the mechanism. But I haven't gotten to the point where we're going to start talking about how do I know if it's going to be SN1 versus SN2? How do I choose proper solvents for those situations, right? The next thing we're going to talk about tomorrow is, right, now now that I know all these factors, how do I choose the right ones to get what I want, right? And that's what we'll start thinking about.
So how to pick these and
How to pick these. If I want to do an SN1 reaction, which solvent should I pick? Right? Which type of nucleophile should I pick? Which type of alkyl halide should I pick? Right? If I want the rate to go faster, what should I pick? Those kind of things. What kind of leaving group should I use? Right? What kind of nucleophile should I use? And it's going to get even more complicated when we do chapter 10. We throw in eliminations. So SN1 and SN2 don't really compete that much with each other, but SN1 and something called E2 do.
well,
And then and that's the second thing we're going to talk about in chapter 10. So aprotic cannot hydrogen bond with themselves. And the other big thing, the example I gave you was protic solvents can surround nucleophiles, right? Remember that? So if you have little F minus, what's easier to surround? F minus or I minus? F minus. So in polar protic solvents, F minus is not a very good nucleophile because it gets surrounded. Right? In polar aprotic, then it's a little more up for debate, which is a better nucleophile. Our book says F minus. I think it's a little less clear in my own opinion. But in protic solvents, for sure, that picture I gave you, that exact example I showed you, right? If I have solvent molecules, right? If I have 5 solvent molecules, you can clearly see, right? Iodine, 5 solvent molecules cannot surround it as well as it can. 5 solvent molecules could surround F minus.
Is that good or bad?
Well, if you want F minus to be your nucleophile, do you want it to be surrounded? No, because you need. So then it's bad in polar protic solvents. So let's put this theory into action. Let's say I present you with. I say you're going to do this reaction in water. And I'm showing you this electrophile. And I'm giving you a choice between CH3O minus or CH3, S minus. I want to know which nuke will react with the alkyl bromide faster. And then, of course, why? So the one that will react the fastest is the sulfur, right? So this is comparing oxygen to sulfur, so we're going down a period, right? And the most important factor in that case, as you go down a period, is size. So sulfur is bigger than oxygen. It's not going to be surrounded as much by the polar protic solvent. And also, since it's bigger, it's going to be more willing to give up its electrons because its electrons are farther outside. So size is most important. Can't be surrounded by the solvent, and it's more willing to give up its electrons. So let's just do the mechanism for this too then, right? Now that we're here, might as well do the mechanism. So this is an SN2 reaction, right? We want a strong nucleophile. For an SN2, we want a strong nucleophile, something that's electron dense, negative charge is good. It's going to attack from the backside, right? Sigma star. And it's going to break that carbon-bromine bond. And we're going to end up with a new carbon-sulfur bond. And we're going to have Br minus over here. Why would this reaction be favored? Why is it going to want to go towards products? Give me some reasons why I'd go towards products. Br minus is more stable with a negative charge than S minus. Probably, right? What else?
No, I just have a question.
The carbon bromine. This is a primary carbon. It's SN2, but on a primary alkyl halide this time. SN2 primary. Okay, so let's just break down that SN2 reaction mechanism versus an SN1. So SN2, you can either have a primary or secondary alkyl halide. That is your electrophile.
But you still want it to be an SP3.
Has to be sp3, right? So it always has to be sp3. I'm doing an SN2 reaction. So I put in a nucleophile, I put in OH minus as a nucleophile. Has to be sp3, has to be primary or secondary, right? So sp3, primary or secondary alkyl halide for the electrophile. Nucleophile, right? We don't want a very big nucleophile. Remember we talked about the size of the nucleophile matters, so we don't want a very big nucleophile for SN2, right? Because we have to get to this sigma star, right? So we don't want the nucleophile to be very big, just like we want the electrophile to be very big, right? So we need skinny nucleophiles to get in there to get that sigma star, right? It all happens in one step, right? One step, so we call this a concerted reaction, right? It does inversion of stereochemistry because it comes from the backside. If this was RS, that stereocenter switches. It goes from R to S or S to R because it comes from that backside, right? One step. So the rate law here as well, the rate equals K, rate constant, times the concentration of the electrophile, the alkyl halide in this case, right? Times the concentration of the nucleophile, the OH minus in this case. So both these things matter in the rate determining step, but there's only one step, right? So that's the rate determining step, right? SN2, nucleophilic substitution bimolecular, meaning there's two molecules in the rate determining step, two reagents, two reactants.
Are they equivalent in the rates?
They are equivalent in the rate, right? So if I double the amount of the electrophile, I double the rate. If I double both, I quadruple the rate. Right? So if I double one, the rate goes times 2. If I double both, it's 2 times 2, the rate goes times 4. They're both directly proportional in the rate. Now, SN1's a little different. SN1, right, again, alkyl halides, but it has to be tertiary, right, has to be tertiary, also sp3, right, In this case, we don't want a very strong nucleophile, so we don't want nucleophiles with negative charges, right? We want something like water, right? It's a bad nucleophile. It's not very nucleophilic, right?
What about size?
So size would matter too, right? So we don't want necessarily a great nucleophile. Usually it's charges. The easiest thing to look for is charges. SN1 reactions will not have negatively charged nucleophiles, ever.
So you don't want a strong, why don't you want a strong?
We don't want a strong nucleophile because in the SN1 case, does the nucleophile matter for the rate? No. So it doesn't really matter how good of a nucleophile we have because the first step in an SN1 reaction is carbocation formation. So the amount of how good of a nucleophile we have doesn't matter, right? The slow step here is forming this carbocation, right? So having a really strong nucleophile doesn't make the SN1 reaction go.
Because you're forming carbocation.
Yeah, because I'm forming carbocation, so yeah. So why?
It's gonna go away.
Yeah, so basically what happens is to do an SN1, you don't want to have a very strong nucleophile, right? Because if you have a strong nucleophile, you certainly can't form a carbocation, right? So this rate determining step, of course, is carbocation formation because, right, RDS, because how fast we form carbocations? Not very fast, they're hard to form, right? So that's the rate determining step. So the rate for an SN1 then is rate times the rate constant times the concentration of the electrophile, which is just the alkyl halide, right?
Doesn't matter if you write alkyl.
You can write alkyl halide, absolutely.